Hello everybody, good morning. Myself Dr. Shubhankar Sen from the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the third lecture of the fourth module of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's class, we shall illustrate the calculation of element level entries for a quadratic bar element. To this end, we shall use the exact integration in the natural coordinate system xi, as well as the Gauss quadrature will also be considered. And we shall close today's discussion by evaluating the shape functions for the quadratic as well as bilinear quadrilateral elements in the natural coordinate system. In the second lecture of this week, we have considered Poisson's equation of heat conduction and we have evaluated the Kij terms for the two-noded bar elements. So, we have used Poisson equation of heat conduction K d2t dx2 plus Q equals to 0 in the second lecture of this week to find Kije and Fie for two-noded bar elements. In today's class, we shall solve the same problem for three-noded or quadratic bar element. In today's class, we shall revisit this problem using three-noded or quadratic bar elements. Consider a quadratic bar element and find K11E. So we shall consider only one illustration for the quadratic bar element. So this is a quadratic bar element with local nodes 1, 2 and 3. This is the xi direction. This is xi equals to 0. This is xi equals to 1 and this is xi equals to minus 1. The shape functions are psi1 is xi equals to minus half xi into 1 minus xi. Psi2 is xi equals to 1 minus xi square and psi3 is xi equals to half xi into 1 plus xi. Now, our expression for Kije was k into integration over omega e d psi ie dx d psi je dx, which we have already shown it comes as 2k by delta x integration minus 1 to 1 d psi ie d psi je d xi. So when I equals to 1 and j equals to 1, we get K11E equals to 2k by delta x integration minus 1 to 1 d psi1e d xi whole square d xi. Now psi1e xi equals to minus xi by 2 plus xi square by 2. This gives d psi1e xi d xi equals to minus half plus xi equals to xi minus half. This can be written as 2k by delta x integration minus 1 to 1 xi minus half whole square d xi equals to 2k by delta x integration minus 1 to 1 xi square minus xi plus 1/4 d xi equals to 2k by delta x into integration. After integration, we get xi cube by 3 minus xi square by 2 plus xi by 4 from minus 1 to 1. This can be written as 2k by delta x into 1/3 minus half plus 1/4 minus 1/3 minus half minus 1/4 equals to 2k by delta x 1/3 minus half plus 1/4 plus 1/3 plus half plus 1/4 equals to 2k by delta x 2/3 plus 2/4 equals to 4k by delta x into 1/3 plus 1/4 equals to 4k by delta x into 7 by 12 equals to 7k by 3 delta x. Now, this is the correct term if we remember the conduction matrix for the quadratic bar element. We have already solved some problems. In week 3, we got our conduction matrix was Ke equals to 7k by 3 delta x minus 8k by 3 delta x, k by 3 delta x minus 8k by 3 delta x, 16k by 3 delta x minus 8k by 3 delta x, k by 3 delta x minus 8k by 3 delta x and 7k by 3 delta x. So this was the conduction matrix. We have already shown this using quadratic bar element. So we were trying to find out the first term K11E. So this is the term K11E 7k by 3 delta x which is matching. Now let us go for the Gauss quadrature for the same integration. Gauss quadrature. Okay. So here Kij equals to 2k by delta x integration minus 1 to 1 d psi I is I d psi d psi 2 is I d psi d psi. Now this integrand we represent by the function Fij. Now it simplifies as 2k by delta x integration minus 1 to 1 Fij xi d xi. For I equals to 1 and j equals to 1, our K11E is 2k by delta x integration minus 1 to 1 F11 xi d xi. Now d psi 1e d xi xi minus half, and d psi 2e d xi equals to d xi of 1 minus xi square equals to minus 2 xi. Therefore, d psi 1e d xi whole square equals to xi minus half whole square equals to xi square minus xi plus 1/4. So, for this case, this is a plus b xi plus c xi square type of expression. It means that this is a parabolic function for which p equals to 2. Therefore, ngp equals to p plus 1 by 2 equals to 2 plus 1 by 2 equals to 1.5 equals to 2. This is the nearest higher integer. Therefore, we have to use a 2-point quadrature. So, use 2-point quadrature for quadratic bar element. This is our bar element. This is xi. So, this is xi equals to 0, xi equals to 1, local node 3, this is local node 2, this is xi equals to minus 1, this is local node 1. Our integration points, these are our integration points or Gauss points. So these are the Gauss points whose coordinates are xi equals to minus 1 by root 3 and xi equals to 1 by root 3. So 1 by root 3, we take it as 0.5778. So we have 2-point quadrature or 2 Gauss points. So this we write as 2k by delta x summation I equals to 1 to ngp f11 xi wi equals to 2k by delta x, where I is varying from 1 to 2, f11 xi wi equals to 2k by delta x f11 at xi1 into w1 plus f11 at xi2 into w2. Now, when we have two Gauss points 1 and 2, the Gauss weights, it is distributed evenly between these two Gauss points. So we get w1 equals to 1 and w2 equals to 1. These are the Gauss weights for 2-point quadrature. So this can be simplified as 2k by delta x f11, this is xi square minus xi plus 1/4. This should be evaluated at xi1. Xi1 means minus 1 by root 3 into Gauss weight is 1 plus f11 is the same function. It should be evaluated at the second Gauss point. So it is xi square minus xi plus 1/4 to be evaluated as xi equals to 1 by root 3 multiplied by the Gauss weight. So this gives us 2k by delta x into minus 1 by root 3 whole square. This is 1 by 3. Then minus xi, it gives us 1 by root 3 plus 1 by 4 plus 1 by root 3 whole square is 1 by 3 minus xi is minus 1 by root 3 plus 1/4. This gives us 2k by delta x into 1/3 plus 1/4 present 2 times. So we have 4k by delta x into 7 by 12 equals to 7k by 3 delta x. So we are getting exactly the same term which we have just obtained by using exact integration. Similarly, we can find out the other terms of the matrix. We can certainly find out k12e, k13e, so on, and the load vector components f1e, f2e, and f3e. Now we shall show some simple illustrations of the use of the natural coordinate system for post-processing purpose. So let us consider problem 1. Let us consider a bar element E whose global coordinates are given as x1e equals to 5, for example, and x2e is given, for example, as 7.5. So this is local node 1, this is local node 2. Now let us take an arbitrary point P here whose actual coordinate is 5.3. So the question is that find the xi value of point P. So this is the global coordinate system. Now let us use the x xi transformation formula. X equals to xm plus delta x by 2 into xi. Here for this particular problem, xm equals to x1e plus x2e by 2. So this is 5 plus 7.5 by 2 equals to 12.5 by 2 equals to 6.25, and mesh size delta x equals to x2e minus x1e equals to 7.5 minus 5 equals to 2.5. So for point P, our x coordinate is already given as 5.3, x mid equals to 6.25, delta x is given as 2.5 by 2 into xi. So this gives us 5.3 minus 6.25 into 2 divided by 2.5. This is our xi coordinate. So by evaluating this expression, we can find the corresponding natural coordinate of point P. Certainly we can understand from this calculation that xi will be a negative quantity. Now let us consider that temperature at node 1 T1E equals to 100 degrees centigrade, T2E equals to, let us take as 80 degrees centigrade. So what will be the temperature at point P? This we can certainly solve by using the global shape functions, the local shape functions, as well as shape functions in the natural coordinate system. So Tx equals to summation of Tje psi j x. Then we can write it as, for j equals to 1 to nen, equals to 2. So T equals to T1e psi 1e x plus T2e psi 2e x. This gives T at, this is T1e is 100 degrees centigrade, 100 into x2e minus x by delta x, where x equals to 5.3 plus T2e is 80, 80 into x minus x1e by delta x, where x equals to 5.3. So this gives us T at 5.3 equals to 100 into x2e is 7.5 minus, here x is 5.3, our delta x is 2.5. The second portion is 80, x is 5.3 minus x1e, this is 5 divided by 2.5. So by calculating, we can find this temperature at point P. Now, using the equation of straight line without using the shape function also, this temperature can be found out. So, using the global coordinate system, the temperature at point P can also be determined using the equation of a straight line. So we can write it as T minus T1e by T2e minus T1e equals to x minus x1e by x2e minus x1e. Here, temperature is the unknown quantity. At the right node, temperature is 80 degrees centigrade, that is T2e, so this is 80. At the left node, that is T1e, temperature is 100 degrees centigrade, so this is 100. The node of interest is x equals to 5.3. x1e is the left node, so for it coordinate is 5, and x2e is the rightmost node. Its coordinate was 7.5 and x1e is 5. So from here we can find out the temperature. Now we can find out the gradient of the temperature within this element. So let us consider, find out dt dx at x equals to 5.3 using natural coordinates. Okay, so dt dx equals to dt d xi into d xi dx equals to d dx of summation of t j psi j equals to 1 to nen into d xi dx. So this comes as, this is d xi, so this comes as t1e d psi 1e d xi plus t2e d psi 2e d xi. This d xi dx, this is 1 by determinant of the Jacobian matrix. Now our psi 1e is half of 1 minus xi. So d psi 1e d xi equals to minus half. It is a constant. It does not depend on the xi coordinate. Similarly, psi 2e xi equals to half of 1 plus xi, and its derivative is d psi 2e d xi equals to half. So T1e was given as 100 degrees centigrade. Now d psi 1e d xi, this is minus half. T2E was 80 degrees centigrade and d psi 2E d psi, this is half. Now determinant of Jacobian, this is delta x by 2. So this is 1 by delta x by 2. So this is equals to minus 50 plus 40 into 2 by delta x equals to minus 10 into 2 divided by 7.5 minus 5 equals to minus 20 divided by 2.5 equals to minus 8. So we find that the temperature gradient within the element, it is independent of the xy coordinate. It is a negative quantity. Therefore, heat flux within the element Q at any x or xy location equals to minus k dt dx equals to minus k into minus 8 equals to 8k. So we have shown that by using the correspondence between the actual coordinate or the global coordinate x and the natural coordinate xy, we can find out the temperature at any intermediate point, the temperature gradient at any intermediate location. So similarly, for a given xy coordinate, we can find out the corresponding x coordinate. Now we have shown these problems with respect to the two-noded bar elements. This can be certainly extended to the three-noded or quadratic bar elements or even for the higher order elements. Now we shall construct the Lagrangian shape functions for bilinear as well as quadratic, quadrilateral elements. To this end, we shall take help from the two-noded as well as three-noded bar elements respectively. Let us begin with the two-noded bar element. So this is a two-noded bar element. Its local nodes are 1 and 2. Its mesh size is delta x. So this is the local coordinate system, and then we can consider its shape function as psi 1e x bar equals to 1 minus x bar by delta x and psi 2e x bar equals to x bar by delta x. Now we can consider a vertical counterpart of this same element. So this is element E, local nodes 1 and 2. This is the y bar axis. So the mesh size here is delta y. In this case, we can define the shape function as psi 1e y bar equals to 1 minus y bar by delta y and psi 2e y bar equals to y bar by delta y. So in the previous weeks, we have mentioned that the tensor product or outer product of two-noded bar elements can be used to construct the shape functions for the four-noded quadrilateral elements or for the higher order elements which are of Lagrangian type. So we shall use the outer product of these two sets of shape functions for constructing the shape functions of bilinear quadrilateral elements. The vertical element with local nodes 1 and 2 and outer product with the horizontal element with local nodes 1 and 2, it will give us the quadrilateral element E, for which we shall do the numbering as 1 1, 1 2, 2 1 and 2 2. This one and this one, it corresponds to 1 1. This one and this 2, it corresponds to 1 2. Similarly, this 2 and this 1, it corresponds to 2 1. And this 2 and this 2, it corresponds to 2 2. Now, they are the local nodes 1, 2, 3 and 4. So this is local node 1, this is local node 2, this is local node 3 and this is local node 4. Now we construct the interpolation functions as construction of interpolation or shape functions for a bilinear quadrilateral element is obtained as this is the outer product or tensor product. So we have the column vector. This is 1 minus y bar by delta y bar by delta y, and this is the row vector 1 minus x bar by delta x and x bar by delta x. This output we can write here as 1 minus y bar by delta y into 1 minus x bar by delta x. Then first row, second column, this gives us 1 minus y bar by delta y into x bar by delta x. Then we have second row, first column. So this is y bar by delta y into 1 minus x bar by delta x. And finally we have second row, second column. So this is y bar by delta y and x bar by delta x. So this is the 2 by 2 matrix. Now this is the output. This matrix terms, it can be written, the matrix entries or terms may be recognized as 1 1, 1 2, 2 1, 2 2. Now 1 1 corresponds to local node 1. Similarly 1 2 corresponds to local node 2. So 2 1 corresponds to local node 4 and 2 2 corresponds to local node 3. So the product, we can represent it as the outer product of shape functions can now be interpreted as one minus x bar by delta x into 1 minus y bar by delta y. The second term was 1 minus y bar by delta y into x bar by delta x, 1 minus x bar by delta x, y bar by delta y, x bar by delta x, y bar by delta y equals to psi 1e, psi 2e, psi 3e, psi 4e. So here we can see a clockwise arrangement of indices 1, 2, 3 and 4 while identifying the shape functions. So we can summarize here psi 1 e x bar y bar equals to 1 minus x bar by delta x into 1 minus y bar by delta y. Psi 2e x bar y bar equals to x bar by delta x into 1 minus y bar by delta y. Psi 3e x bar y bar equals to 1 minus x bar by delta x into 1 y bar by delta y, and finally psi 4e x bar y bar equals to x bar by delta x into y bar by delta y. Now let us solve a simple problem using the local coordinate system for bilinear quadrilateral elements. So this is for psi values of bilinear quadrilateral elements using local coordinates x bar, y bar. So let us solve a problem. So let us consider a square element. This is element E. It has 4 nodes, 1, 2, 3 and 4. Let us consider the global coordinates as 1, 2, 2, 2. Its coordinates are 1, 3, and then finally this coordinate is 2, 3. Then x1 e equals to 1, y1 e equals to 2, x2 e equals to 2, y2 e equals to 2, x3 e equals to 2, y3 e equals to 3, x4 e equals to 1, and y4 e equals to 3. These are the global coordinates. Global coordinates. Also, we are given T1 e equals to 100 degrees centigrade, T2 e equals to 90 degrees centigrade, T3 e equals to 80 degrees centigrade, and T4 e equals to 70 degrees centigrade. For instance, let us take an arbitrary point inside and let us denote that point as point P. Let us consider its coordinate as 1.62 and 2.3. So find the value of temperature at point P. So the data of coordinates which we have been given, they are in the global coordinate system. We can use the local coordinate system. We can update all the coordinates in the local coordinate system, including those of point P, and then by using the trial solution expression, we can find out the temperature at point P. So let us first show the global coordinate system. This is the global coordinate system xy, and here we have the element. This is element E. Local coordinate system is shown like x bar, y bar. So this distance is x1e and this height is y1e. Local node 1, local node 2, local node 3, local node 4. Now if we look at the data, we can understand that the mesh size in both the directions, this is of unit value. It means that delta x equals to 1 and delta y equals to 1. So the coordinates for this element will be like 0, 0, delta x, 0, delta x comma delta y, 0 comma delta y. So these are the coordinates of all four corners. Now we have point P here. For point P, for point P, we use the relation x equals to x bar plus x1e. So x for point P, x bar for point P plus x1e. Now x of point P was 1.62, x bar P is unknown, and x1e, this is given as unit value. So x1e is 1. So from there we find xp bar equals to 0.62, and similarly we can find out yp equals to yp bar plus y1e. This gives us yp was 2.3 equals to yp bar plus our y1e, it was of 2 unit. This x1e and y1e, they depend on the coordinate of the first node, local node 1. So here y1 equals to 2. This gives us yp bar equals to 2.3 minus 2. So this is 0.3, or therefore the local coordinates of point P are x bar P equals to 0.62, y bar P equals to 0.3. So now we have the data for calculating the temperature at this point P. Small correction here. This is certainly CW. Temperature at point P can be evaluated using the trial solution expression. T at x bar y bar equals to summation of TJE psi JE at x bar y bar. Here we have 4 nodes, so J is varying from 1 to 4 equals to T1E psi 1E at x bar y bar plus T2E psi 2E at x bar y bar plus T3E psi 3E x bar y bar plus T4E psi 4E x bar y bar. Our T1 was 100 degree centigrade, so we can simplify it as 100 psi 1E equals to 1 minus x bar by delta x into 1 minus y bar by delta y. T2E was 90 degree centigrade. 90 into x bar by delta x into 1 minus y bar by delta y. T3E was 80 degree centigrade. 80 into psi 3E is x bar by delta x, y bar by delta y. And finally, our T4E was 70 degree centigrade, and psi 4E is 1 minus x bar by delta x into y bar by delta y. Now x bar equals to 0.62 and y bar equals to 0.3 for point P. Therefore, temperature at x bar equals to 0.62, y bar equals to 0.3, it can be evaluated as 100 into 1 minus 0.62, our delta x is 1, into 1 minus 0.3 by 1 plus 90 into x bar is 0.62, delta x is 1, and 1 minus our y bar, this is 0.3, delta y is 1, plus 80 into x bar is 0.62 by 1, delta x is 1, and y bar is 0.3, and delta y is also 1. Finally, the last temperature is 70 into 1 minus x bar is 0.62, delta x is 1, y bar is 0.3, and delta y equals to 1. So, we can calculate this and find out the temperature at this intermediate point. Okay, so this calculation is left out here for your practice, and here we are given delta x equals to 1 and delta y equals to 1. Now we shall evaluate the shape functions in the natural coordinates using the tensor product or outer product from shape functions of the two-noded as well as three-noded bar elements. Lagrangian shape functions for bar elements in global or actual and natural coordinates. So there is a standard expression for shape function evaluation of the bar elements of any order. This can be defined using the global coordinates as well as the local coordinates. So before providing the expressions, we first define the product operator. So the way we define the summation operator, I varies from 1 to n. This gives us a1 plus a2 plus a3 plus an. This is the summation operator. Similarly, we have a product operator denoted by the symbol capital pi. So here the product operator operating on ai, where I is varying from 1 to n, this indicates a1 into a2 into a3 into an. So this is the product operator denoted by capital pi. Now we can define the Lagrangian shape functions for a bar element. For a bar element, we define psi ie as a function of x. This is the shape function of n minus 1th order equals to the product operator of xk minus x divided by xk minus xi. Here k is varying from 1 to n such that k is not equals to I. So this is the basic definition of shape functions of Lagrangian type for one-dimensional bar elements. For Lagrangian shape functions, we can expand this expression in global coordinates. Expanding this expression, we obtain psi ie x of n minus 1th order equals to x1 minus x, x2 minus x, x I minus 1 minus x, x I plus 1 minus x n minus 1 minus x n minus x. This is the product in the numerator. Similarly, in the denominator, we have an equivalent product where x is substituted by x subscript I. So we just present it as x1 minus xi, x2 minus xi, xi minus 1 minus xi plus 1 minus xi, xn minus 1 minus xi, and finally xn minus xi. Using this relationship, we can find out the shape functions of two-noded bar elements, three-noded bar elements, and of whatever order we want. Any finite order is possible. Now, this expression can be given in the natural coordinate system. Just the x will be replaced by xi or eta depending on whether we are going for the horizontal bar element or the vertical bar element. Now, since k cannot be equals to I, we cannot take the term xi minus xi, and because of this, here we have to note that the term xi minus xi is not included. Okay, we cannot divide by 0. This should be noted. Now, in natural coordinate system xi, we can write it as psi ie n minus 1 xi equals to the product operator xi k minus xi k minus xi I. K is varying from 1 to n and k is not equals to I. This gives us xi 1 minus xi 2 minus xi I minus 1 minus xi I plus 1 minus xi n minus 1 minus xi n minus xi. At the denominator we have xi 1 minus xi I, xi 2 minus xi I minus 1 minus xi I plus 1 minus xi n minus 1 minus xi n minus xi. Now we have the expressions of shape functions, the generalized expression for the bar elements. Now the expressions for shape functions of two-noded bar elements can be used to construct the bilinear quadrilateral master element in the natural coordinate system. So construction of the bilinear quadrilateral master element in the natural coordinate system using the linear or two-noded bar elements. So consider a two-noded horizontal bar element, the local nodes being 1 and 2. This is the xi direction. This is xi equals to minus 1. This is xi equals to 1. This is xi equals to 0. Here, shape function is psi 1 is xi equals to half of 1 minus xi, and psi 2 is xi equals to half of 1 plus xi. Similarly, we can define the element in the vertical direction. So this is the eta direction. This is eta equals to minus 1. This is eta equals to 1. Local nodes 1 and 2. This is eta equals to 0. So psi 1 e eta equals to half of 1 minus eta and psi 2 e eta equals to half of 1 plus eta. Now we can take the outer or tensor product of these two elements and construct the bilinear quadrilateral master element. Okay, so this is the outer or tensor product. This product will give us first row, first column. So this gives us half of 1 minus eta into half of 1 minus xi. Then we have first row and second column. So this is half of 1 minus eta into half of 1 plus xi. Next we have second row, first column. Then we have half of 1 plus eta into half of 1 minus xi, and finally we have the second row, second column. So half of 1 plus eta into 1 plus xi. So these terms, like the previous case, can be written as 1 1 1 2 2 1 2 2. This can be written as psi 1 e, psi 2 e, psi 3 e, and psi 4 e. So this is the clockwise numbering in the output of the tensor product. So we get psi 1 e in the natural coordinate system, xi eta equals to 1/4 into 1 minus xi into 1 minus eta. Psi 2 e xi eta equals to 1/4 into 1 plus xi into 1 minus eta. Psi 3e as a function of xi and eta equals to, here half was missing, equals to 1/4 into 1 plus xi into 1 plus eta, and finally psi 4e xi eta equals to 1/4 into 1 minus xi into 1 plus eta. These are the shape functions for the bilinear quadrilateral elements. They are of the form psi of xy equals to a plus b xi plus c eta plus d xi eta. Okay, so they are already matching with the profile predicted from the Pascal's triangle. Now our bilinear quadrilateral element, that is constructed by taking the outer product of the two noded bar elements. This is the master element. We denote by the symbol omega e cap. Its local nodes are 1, 2, 3, and 4. So we construct the coordinates from the coordinates of the corresponding two noded bar elements. So this coordinate is -1, -1. Here xi is 1, eta is -1. Here xi is 1, eta is 1. Here xi is -1 and eta is 1. So this is the origin of the natural coordinate system. This is 0 0. So this is xi axis, this is eta axis. So this dimension is 2 unit and this dimension is also 2 unit. So this is the master square element in the natural plane, natural or xi eta plane for 2 dimensions. Similarly, we can extend it to the 3-dimensional cases Now, with the aid of these coordinates, we can give a generalized expressions for these shape functions. These four expressions can be represented via a compact form psi ie psi eta equals to half of 1 plus psi I psi into half of 1 plus eta I eta, where I varies from 1 to 4. When we put I equals to 1, then we get psi 1e psi eta. Then in the right hand side first term, we have to write 1 plus psi 1 psi. Now psi 1, in this case, it is minus 1, and half of 1 plus eta I eta for the first local node, eta I is also minus 1. So easily we understand that we get the desired product 1/4 of 1 minus xi into 1 minus eta for the first shape function. Here it is CW. Now we have already discussed the Pascal's triangle using the global coordinate system. We can now illustrate briefly the counterpart of this Pascal's triangle using the natural coordinate system. Pascal's triangle in the natural or xi eta coordinate system. So this is the xi axis, this is the eta axis, xi axis, eta axis. At the intersection of xi axis and eta axis, we get a single noded bar element. So this is 1, where xi to the power 0 and eta to the power 0, they give us 1. Then this is the xi axis for the bar elements, and then the polynomial components for the bar element, they will go as xi, xi square, xi cube, xi to the power 4, xi to the power 5, and so on. Similarly, along the eta direction, the components of the polynomial or components of the bar element, they will come as eta, eta square, eta cube, eta to the power 4, and eta to the power 5. We can draw parallel lines with the respective coordinates, and we can find out the intersection points, and then we can locate the elements of quadrilateral type or of triangular type. So we shall show some cases. Here, this is the intersection of xi and eta, where both of them are having single power or unit power. So this coordinate will be xi eta. Along this axis, xi square is constant. So we get here xi square. Here eta is constant, so it is xi square eta. So this should be xi cube eta, and this should be xi to the power 4 eta. Here this xi is constant, so this is xi, and eta is eta square, so this is eta square. So this is xi square eta square. This is xi cube eta square. This is xi to the power 4 eta square. When we come to the next row, this becomes xi eta cube, xi square eta cube, xi cube eta cube, xi to the power 4 eta cube. Then here we have xi eta to the power 4, xi square eta to the power 4, xi cube eta to the power 4, xi to the power 4, eta to the power 4. Here we get xi eta to the power 5, xi square eta to the power 5, xi cube eta to the power 5, xi to the power 4, eta to the power 5, and so on. So we have already constructed the bilinear shape function for this first case, where we have the format of psi equals to a plus b xi plus c eta plus d xi eta. If we go to the next level, then we have the quadratic quadrilateral element. So this will illustrate the quadratic quadrilateral elements where we have 9 nodes. So we have identified the nodal locations. Now using the quadratic shape function for the bar elements, we can construct the shape functions for the quadratic quadrilateral element. So use the shape functions of quadratic bar elements, take their outer product or tensor product to construct the quadratic quadrilateral element and their shape functions. There will be 9 shape functions for the quadratic quadrilateral element because of the 9 nodes. So now we consider the quadratic bar element in the vertical direction and in the horizontal direction. This is the xi direction, this is the eta direction. Local nodes are 1, 2, 3. Here local nodes are 1, 2 and 3. This is the outer product. So here the shape function is psi 1 e xi equals to minus xi by 2 into 1 minus xi. Psi 2 e xi equals to 1 minus xi square. Psi 3 e xi equals to xi by 2 into 1 plus xi. Psi 1 e eta equals to minus eta by 2 into 1 minus eta. Psi 2 e eta equals to 1 minus eta square, and psi 3 e eta equals to eta by 2 into 1 plus eta. Now with the help of this outer product, we can construct the quadratic quadrilateral element as well as the shape functions. So let us first illustrate the quadratic quadrilateral element. So it has 9 nodes. These are the nodes. There is one internal node. Now these nodes are given as 1 1, 1 2, 1 3, 2 1, 2 2, 2 3, 3 1, 3 2, 3 3. Now we can assign the local node numbers indices 1 to 9 with every local node. Okay, so local node 1, local node 2, local node 3, local node 4, local node 5, local node 6, local node 7, local node 8, and finally the local node 9. Now we can construct the product of these shape functions. This product gives us, so we can write it as minus eta by 2 into 1 minus eta, 1 minus eta square, eta by 2 into 1 plus eta. This is the first column of the vertical shape functions. This is giving us 3 row, 1 column. The outer product with the row vector in terms of xi. So this is minus xi by 2 into 1 minus xi. This is 1 minus xi square, and this is xi by 2 into 1 plus xi. So this is 1 row, 3 column. This will give us a 3 by 3 matrix. So let us construct it. First row, first column. So this gives us xi eta by 4 into 1 minus xi into 1 minus eta. Now, first row, second column, it gives us minus eta by 2 into 1 minus eta into 1 minus xi square. Finally, we have minus xi eta by 4 into 1 minus eta into 1 plus xi. For the second row, we have minus 1 minus eta square into xi by 2 into 1 minus xi. Then we have 1 minus xi square into 1 minus eta square. Finally, in the second row, we have 1 minus eta square into xi by 2 into 1 plus xi. In the last row, we have minus xi eta by 4 into 1 minus xi into 1 plus eta. The next term is eta by 2 into 1 minus xi square into 1 plus eta, and the final term is xi eta by 4 into 1 plus xi into 1 plus eta. So this is the closure of the 3 by 3 matrix for the quadratic or biquadratic element in the natural coordinate system. So this is our xi axis, this is our eta axis, this coordinate is -1, -1, this coordinate is 1, -1, this coordinate is 1, 1, and this coordinate is -1, 1. So our structure of the matrix form is the shape functions can now be identified from 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. It corresponds to 1, 1. This is corresponding to local node 1. So this will give us psi 1e. 1, 2 corresponding to local node 2. This will give us psi 2e. 1, 3 corresponds to local node 3. This will give us psi 3e. Next we are having 2, 1. 2, 1 is giving the correspondence with local node 4. It is giving us psi 4e. 2, 2, it is corresponding to local node 5. So this gives us psi 5e. Next we get psi 6e for 2, 3. And finally for 3, 1, 3, 2 and 3, 3 we get psi 7e, psi 8e and psi 9e in the xi eta plane to get. Now we can write these individual shape functions as psi 1e xi eta equals to xi eta by 4 into 1 minus xi into 1 minus eta. Psi 2e xi eta equals to minus eta by 2 into 1 minus xi square into 1 minus eta. Psi 3e xi eta equals to minus xi eta by 4 into 1 plus xi into 1 minus eta. Psi 4e xi eta equals to minus xi by 2 into 1 minus xi into 1 minus eta square. Psi 5e xi eta equals to 1 minus xi square into 1 minus eta square. This is psi 5e. So then we have psi 6e equals to xi by 2 into 1 plus xi into 1 minus eta square. psi 7e xi eta, this is the function of xi eta, equals to minus xi eta by 4 into 1 minus xi into 1 plus eta psi 8e xi eta equals to eta by 2 into 1 minus xi square into 1 plus eta, and psi 9e equals to xi eta by 4 into 1 plus xi into 1 plus eta. In this manner, we can construct the higher order interpolation functions for the quadrilateral elements. So, we conclude today's class here. In today's class, we have obtained K11E term for a quadratic bar element using exact integration and Gauss quadrature in the natural coordinate system. We noted that the Jacobian matrix in one dimension Je equals to dx dxi 1 by 1. So dx dxi ratio is a ratio of lengths. The determinant of Je equals to dx dxi equals to ratio of lengths of elements or segments in the actual or physical coordinate, and that in the natural coordinate. Since the lengths will be always positive quantities, from here we understand that the determinant of the Jacobian matrix, it should be a positive quantity, and then we cannot divide by 0. It means that the determinant of the Jacobian matrix, it cannot be 0. So determinant of the Jacobian equals to delta x by 2, it cannot be 0, or the value of the Jacobian matrix determinant, it should not be close to 0. Finally, we constructed the shape functions for bilinear and biquadratic quadrilateral elements in xi eta plane using bar elements shape functions. For today's class, I recommend the texts of Professor T.J.R. Hughes and Professor J.N. Reddy. Thank you very much for attending today's lecture.